Okay, today we're going to continue Chapter 9. We're going to look at sections 9.3 and 9.4, and this goes over three new tests for convergence and divergence. We have the integral test, we have the p-series test, and we have what's called the comparison test in Section 4. So Section 3 starts off with the integral test and the p-series test. Calculators out the way. Okay. Okay. So to begin with, we look at the integral test. And so we start off with a sum, n equals 1 to infinity. And it may be 0, maybe 2. There could be some a little bit different changes here. Just we want to keep in mind what this number is. And inside we have our expression a sub n, whatever that happens to be. So if we start off with a series such as this one, there we go. The idea is, can we create a function based on what is essentially a discrete formula? We call a sub n a discrete formula because it only works for the letter or for the values 1, 2, 3, 4, 5, etc. But if we create a function, it's going to have to be true for every value in between. So we know a function is going to be, we're going to want this function to be continuous. So first thing we do is create a function f of x based on a sub n. Now, what that essentially means is we're going to take the n inside this formula and change it to x. And that'll be what f of x is equal to. Okay. Next thing we do is check if f of x is continuous, positive, continuous, and decreasing for x greater than or equal to 1. Now the reason we say x greater than or equal to 1 is that corresponds to n equals 1 here. So effectively, whatever number this summation starts at, that's the value that we're interested in right here. So it may be that our function is not continuous at a certain point, but that certain point is prior to that first value of the series, and that's acceptable. As long as it's continuous for every value greater than or equal to that number, we're alright, as well as being positive term and decreasing. Once we've verified those three things are true, next we integrate f of x from 1 to infinity. But again, the limits of integration here will match the limits on this series here. So if this one starts at 2, then this has to be true for x greater than or equal to 2, and this one has to start at 2 also. And that's something that we want to keep in mind. So we check all these things, we find this integral, and lastly, whatever behavior the integral has, then our series has the same behavior. What that means is if the integral converges, then the series converges, and if the integral diverges, then the series diverges. Second, if the integral diverges, so does the series. Essentially, they have the same behavior, so whatever behavior the integral displays, then the series will display as well. Now, one thing I want to note here is that whatever value the integral converges to, like we might find this integral and it comes out to be a 4. That doesn't mean that the series adds up to a 4. There's actually no connection between the two. The only connection we know is if this converges, so does this. But we won't know what number this actually converges to without a lot of further investigation. So it is worth mentioning that there's no connection to what number it converges to the series. Okay. Now, for the purposes of the exam, I'm not going to have you check positive, continuous, or decreasing. In general, like in our homework, we would like to go ahead and check that, but that's not something I'm going to have you do when it comes time to take the exam on this material. So just keep that in mind. The way that we check if a function is positive and continuous, we can check that just by looking at the function, generally speaking. We can tell if it's going to be positive or negative based on the interval that it needs to be true over. And we can tell where it's discontinuous because of the type of function it is. Usually if it's like rational, we know the denominator can't be 0. Or if we have a square root and we can't take a square root of a negative, that's really the main things we're looking for. Or if it, now for decreasing is a little more tricky. Generally, if we can show that the derivative is negative, that means it's a decreasing function. So let's look at an example. This is problem 4 on page 613. With a sum n equals 1 to infinity of 2 over 3n plus 5. Okay. So first of all, that means we'll have f of x equals 2 over 3x plus 5. So again, we just changed the n to x. And this is from 1 to infinity, so we can say x greater than or equal to 1. Now, first, if we think about it being positive, if we plug in a number that's bigger than 1, 2 will be positive, and for a number that is bigger than 1, 3 times a positive number plus 5 will be a positive number. So we end up with a positive divided by positive, which is positive. So we can just check that one off. Continuous, this is the next thing we need to check. Well, we know this is a rational function and it's discontinuous when the denominator is 0. Now, in this case, that happens at negative 5/3. So it's discontinuous at negative 5/3, but the question is that part of our domain? Well, our domain that we're focused on is x bigger than or equal to 1. And since negative 5/3 is not inside that domain, we're good. Okay. Now, as I said, the more complicated one is the decreasing part. Because in this case, we'll have to take the derivative. So what I'll do is I'll take the function here and write it as 2 times 3x plus 5 to the negative 1. That way it'll be a little bit easier to take the derivative. So f prime of x will be negative 2 times 3x plus 5 to the negative 2 times to the derivative inside, which is 3. And so that's equal to negative 6 over 3x plus 5 squared. Now we look at this term. We have a negative number on top. On the bottom we have a number that's being squared, which is guaranteed to be positive. So negative divided by positive is equal to a negative. So it's less than 0. And it's decreasing since f prime of x is less than 0. If you remember back in, I can't remember if it was chapter 2 or chapter 3 when you're in Cal 1, we demonstrated that the value of the derivative, or specifically the sign of the derivative, tells us whether it's increasing or decreasing. A positive derivative means increasing and a negative derivative means decreasing, and that's what we verified here. It is a negative derivative, and not just for our interval, but for every value of x, and except negative 5/3, which is undefined, but again not in our domain. So that means the function is decreasing where we need it to be. So all of that is just preparation and saying that we can actually complete the integral test and have it be a meaningful result. If these three things aren't true, then whatever we get from integrating the function, it doesn't really amount to anything. Okay? So we want to make sure these three things are valid before we move on. Okay. So now we can integrate. So we want the integral of 2 over 3x plus 5 from 1 to infinity. Now technically these will all be going to infinity, so they should be improper integrals, as we saw on our last exam. By the way, with the last exam I'm about halfway through it, so I should finish by tomorrow with those grades, so you'll be able to see them before the weekend. I do apologize for taking so long, but I want to make sure that I get through everything in a and not try to go too quickly and skim over things. Just give everyone a fair chance. Anyway, but I'll make sure I have that done by tomorrow, and I will be leaving feedback, so like on questions where you miss points. So be sure to look at those and let me know if you have questions on that. Anyway, so back to our problem here. Integral from 1 to infinity of 2 over 3x plus 5 dx. Now, the 2 on top, we can factor that out. And because we have a linear expression down here, we can let u equal 3x plus 5. Even if it wasn't linear, we would use the same approach. I don't know why I said that specifically. But, because it's linear, it's going to be a logarithm. That's what it actually means. Now, the derivative here is 3. But we don't have an extra 3 here for this derivative. Normally, we would expect to see like 3 over 3x plus 5. So we'll take du over 3 and use that to replace dx. Which, a little bit off screen. There we go. Okay. So making our conversion to the u variable, we have 1 over u du, because this is u on the bottom. Now du, well, dx is du over 3, and then I put the du here, and I put the over 3 in front. So this is now a 2/3. Alright, and then we can just integrate 1 over u, which is natural log of u, and plug u back in, which is natural log of 3x plus 5. Okay. Plugging in our limits, 2/3, and then we get natural log of infinity minus natural log of 8. Now, natural log of infinity goes to infinity. That's just the natural log function. As x goes to infinity, the value of the logarithm goes to infinity. Very slowly, but it goes to get there. And so the result is infinite, so it diverges. And then our conclusion is that the series diverges. Again, we know with the integral test, whatever behavior the integral has, and we found that the integral diverged, that means the series will diverge also. Alright, and that's really what we want to find, is what happens to the series ultimately. And that's what the integral test does. We check all three of these things, whether it's positive, continuous, or decreasing. Then we go ahead and integrate the function if all three of those conditions are met. We integrated, did our substitution, and then plugged in our limits, and then we got an infinite number, which means it diverges. And so because the integral diverges, that means the series diverges also. And that's our conclusion here, and that's how we would approach that problem. Okay. Let's see what else we want to work here. Okay, this is problem 8, same page. Now in problem 8, we have the sum n equals 1 to infinity of n times e to the negative 1/2 n. It says n over 2, but we could write it either way. Now, that means our function f of x will be x times e to the negative 1/2 x for x greater than or equal to 1. Let's just go from 1 to infinity. Now, we know this function. Exponential functions are always positive. And multiplying by an x, that means we're not going to ever divide by 0. We'll multiply by, no, we won't even multiply by 0. Yeah, so this should always be continuous and positive. And if we took the derivative, we would also find that is decreasing. I'm going to skip where we show all three of those things here, but we can easily verify those if we go through the same process I outlined on the first question. Instead, let's just focus on utilizing the integral test itself, which means we want to integrate this and see if it converges or diverges. Now, when we look at this, we have a polynomial term x times an exponential term e to the negative 1/2 x. Now, there's two approaches we might be able to take here depending on this function or this expression that we're integrating. One, it could be possible due to substitution. However, normally we would substitute for whatever's in the exponent here, but that only works if the derivative is here, and x has a derivative of 1, not x, so we can't really use the substitution. The alternative is, because we have two different types of terms multiplied together, we can use the integration by parts instead. So u is equal to x, dv is e to the negative 1/2 x dx, du is dx, 1 dx, and v, if we integrate, is negative 2 e to the negative 1/2 x. We get the negative 2 here because we actually divide by negative 1/2 when we integrate, and dividing by negative 1/2 is the same as multiplying by its reciprocal, negative 2. Okay, and our pattern is u times v minus integral v times du. U times v would be negative 2x e to the negative 1/2 x. And then plus, since v is negative, that will make that a plus, 2e to the negative 1/2 x dx. So continuing our integration, this will be, again, when we integrate, we divide by the negative 1/2. So 2 divided by negative 1/2 will be negative 4. So negative 4 e to the negative 1/2 x from 1 to infinity. Now, in both of these cases, well, these two cases, the reason I wrote them separately is that we're going to have to work them separately. When we plug in infinity here, we get negative 2 times infinity, which is negative infinity, and then e, this x is up here, sorry, not down here, and this is e to the negative 1/2 times infinity, which is e to the negative infinity. Now e to the negative infinity if we look at the graph of our exponential function, this is e to the x, then e to the negative infinity, you see is the graph continuing off to the left, and what's happening is we know we have this horizontal asymptote here, so as the graph approaches negative infinity, the value of e to the negative infinity is going to 0. So that's important to remember, that e to the negative infinity goes to 0. Okay. And e to the positive infinity goes to infinity. So what happens here, if we plug in infinity, is we get negative infinity times 0, which is indeterminate. That means we cannot determine the value of that as we currently have it, but we can move things around and turn it into a L'Hopital's rule problem. We know if we plug in the 1, we just get negative 2 or plus 2 times e to the negative 1/2. Over here, things are much more straightforward, because if we plug in infinity, it's just negative 4 times e to the negative infinity, which we already said e to the negative infinity is 0, so it's negative 4 times 0. Then we plug in the 1, and we get plus 4 e to the negative 1/2. Anyway, so this is indeterminate. So what we might do is we write it as negative 2x over e to the 1/2 x. Basically take the e to the negative exponent, drop it down so it's e to the positive exponent. And take the limit as x goes to infinity. Now in this case it's infinity over infinity, so we can use L'Hopital's rule. Okay. Now, taking the derivative on the top and the bottom separately, negative 2 over 1/2 e to the 1/2 x. So we get negative 2 divided by infinity, because e to the infinity is infinity. So eventually we get this to be 0. Okay. So long story short, plugging in infinity here results in a 0. It does take a little more work to demonstrate why that's true, and understanding, like I said, the nature of the exponential function, in that e to the infinity does go to infinity, and e to negative infinity does goes to 0. Okay. So we get 0, and then we plug in our 1, so it's minus 2, well, minus, and then minus 2 times 1 e to the negative 1/2 times 1, so plus 2 e to the negative 1/2, plus, and we plug in infinity here. Now e to the negative infinity is 0 times negative 4, which is still 0. And this will be minus, and then we have a minus 4 e to the negative 1/2 times 1. That makes it plus 4 e to the negative 1/2. So it equals 6 e to the negative 1/2. Now, that's the value of the integral, finally. And it takes a lot to get there. But we know that the integral converges because we got a number besides infinity as the value of the integral, or that it doesn't exist. So we know it exists. It comes out to be 6e to the negative 1/2. Now, from there, we can say since the integral converges, then the series converges as well. So that's our ultimate conclusion, is that the series converges. Okay. So, this does require a little bit more of an understanding about certain transcendental functions, like working with logs, as we did in the first example, and then exponents in this example. We have to know what happens as we continue to the left and to the right in those cases, as far as the evaluation of those numbers. Because we are working with infinite limits of integration, we're frequently going to see that happen. Okay. Now the shortcut here, and we went through this discussion regarding L'Hopital's rule. The shortcut is that the exponential will always determine what happens to the outcome here when we plug in infinity. Exponential will always take precedence over a polynomial. And so whatever the exponential does is really what happens here, which is goes to 0. Because what ends up happening in L'Hopital's rule is the polynomial, no matter what the exponent is, we know that if we keep taking derivatives of an exponential term, we'll still have an exponential term times, in this case, an extra constant. But if we take enough derivatives of a polynomial, eventually it goes to 0, or at least goes down to a constant. So we have a constant divided by infinity, which will always go to 0. So if we have like x to the n times e to the something times x, whatever e does is generally going to determine what happens to that function. Okay. So if we have a negative exponent, it's going to go to 0, and if we have a positive exponent, it's going to go to infinity. So we can use that as a kind of a hint as far as how things are going to go. But ultimately, our conclusion is still based on the series itself, which we haven't looked at from the very first, because we immediately changed it to a function. But this tells us that the series does converge. There's one more I wanted to do. This is number 16. And we have the sum n equals 2 to infinity of 1 over n square root of natural log n inside of our summation. So we'll create our function f of x equals 1 over x square root of natural log x for x greater than or equal to 2. And again, we say x greater than or equal to 2 because that's where the series is defined, 2 to infinity. So we want to make sure this reflects that. Okay. So the question is, let's do this integration from 2 to infinity of 1 over x square root natural log x dx. Now, the problem working with natural log of x, and we've talked about this a fair amount in the last chapter, the problem is that we don't know how to integrate natural log of x by itself outside of integration by parts. Now there is one other alternative, and that is we can potentially make a substitution. If we can substitute for the logarithm instead of doing integration by parts, that would work as well. But really those are our two options. Now the way this problem is set up, I'm almost thinking this will be a substitution more than by parts, because if it's by parts, we'll tend to see the natural log in the numerator. Part of this is just experience as far as working with a lot of different problems and slowly coming to the realization, what is more likely in some cases than others. And it's not something we learn right away necessarily, but at least at this point we have the tools that we need to tackle it, and if it doesn't work one way, then we know we can go the other way with it. But what I would say is ultimately we look at this, because it's in the denominator and is under a square root, it's probably going to be a substitution. So what is the derivative of natural log of x? Well, if we take the derivative of natural log of x, we know that's 1 over x dx. And we look at the integral and we see, okay, do we have 1 over x times dx anywhere in this integral? And in fact we do. 1 over x times dx is basically the rest of the integral that's outside the square root. So this is our u, so we have square root of u on the denominator, and then our du is the rest of this, of 1 over x times dx. So we end up with du over square root u. So the substitution does work in this case. Now before we integrate that, we'll probably want to go ahead and change that to a u to the negative 1/2 rather than 1 over the square root of u like we have. And we can integrate that. That'll be u to the positive 1/2 divided by positive 1/2, and then evaluated from 2 to infinity. Now if we divide by 1/2, that's the same thing as multiplying by 2. And u to the 1/2 is square root of u. Now we can plug back in u, which is natural log of x. So we end up with 2 square root of natural log of x from 2 to infinity. And if we plug in those limits, we get 2 square root of natural log of infinity minus 2 square root natural log of 2. But the question is here, what is natural log of infinity? Does it become infinite, or does it converge to a value? Because that's ultimately going to determine what happens in this problem. Let's look at the graph of natural log of x. Natural log of x looks like this, and we can tell as it goes to 0, it's going down to negative infinity. Okay, specifically 0 from the right, so we want to keep that in mind. Go into negative infinity, and as the graph continues up here, As x goes to infinity, the y value goes to infinity also. So natural log of infinity goes to infinity. And that's really the fact that we want to remember for logarithms, is that as we continue towards infinity, the value of the logarithm goes towards infinity also. And so that means that this result will still be infinite. Okay? And because it's infinite, we know that it diverges. Therefore, the series diverges also. Okay. Are there questions on that? Okay. So that's our integral test. Let's look at p-series next. Now, we define a p-series as being the sum n equals 1 to infinity of 1 over n to the p power. And in this case, 1, it converges if p is greater than 1, and 2, it diverges if p is less than or equal to 1. This honestly is about as easy as these problems get, looking at a p-series. This will be more significant when we move on to section 4 and use these as comparisons with what we call our comparison test. But for now, we're just introducing a relatively simple idea. All we have to do is look at the value of the exponent and then determine if it's converging or diverging based on that. Again, we don't know exactly what it diverges to. 1 over n squared, for instance, I believe converges to pi squared over 6. I've actually seen a proof for that. It's pretty crazy. I don't know if I have that where I can post it for you. But anyway. So for example, if we have sum n equals 1 to infinity, 1 over n squared, in this case, p is equal to 2, which is greater than 1, so it converges. Now we want to be careful, because we can overthink it in some cases. So if we say that we have the sum of n cubed, we look at that and we think, oh, p is 3, it must converge. But remember, it's written 1 over n to the p value. So if we write that as a fraction, that's 1 over n to the negative 3 if we move it to the bottom. So p is negative 3, which is less than or equal to 1. I didn't even write that comma there. So it diverges in this case. Unfortunately, there's not a lot more complexity to it than that. Sometimes we'll try to trick you by saying like the square root of n cubed or something, but that's about as difficult as these get. Alright, so that's our p-series, and I'll give you a couple of problems where you can test that out. beyond that, I don't have anything else there for that section. Unfortunately, I'm just not feeling well today, and I've been trying to push through class, but I'm going to have to stop it there. Let me give you some homework to look at. 3. Well, that looks terrible. I'm not going to give you that one. Goodness. Look at 7. 19. 33. 37. And that should be good for the 2 rules there. Anyway, I'm sorry to stop early like that, but I'm about to have a problem. So we're gonna stop there. Y'all take care. Like I said, I should still have a test graded tomorrow. I'll talk to y'all Tuesday. Y'all have a good day.